Hi everyone. Today we're doing lesson 5.2 on exponential decay. We're going to start off with a simple exploration example. Consider a car that is said to lose 6.5% of its value each year. If a car is purchased for $23,620, we want to write a recursive sequence that gives the value of this car after n years. So let's start off with a sub 0, which is equal to $23,620. So how much is the car going to be worth after n years? Well, it's going to be worth the value of the previous year, a sub n minus 1, times some value. If it loses 6.5%, well, that means it keeps 93.5%. So to find the value of the car, I could just multiply by 0.935, such that n is greater than or equal to 1. So just make sure we're good on this. If it loses 6.5%, it keeps 93.5%. So to know the value, I'll just multiply by that percentage. And I could multiply by parentheses 1 minus 0.065. So it has 100% and it loses the 6.5%. That's what I have here in this expression. But if I simplify that, I get the 0.935. So excellent. So let's look at this way. Let's do another t-chart where I have n years passing. And then I have the value of the car being my output y. So this will be n and y. So in the 0th year, I've got $23,620. Let me put that up here. After 1 year, if I take that 23,620 and I multiply that by 0.935, I have the value of the car is $22,084.70. So going down a little bit. After 2 years, I multiply again by 0.935. I get 20,649.2. So it's easy to see that this is not decaying at a linear rate because the differences in these y values is not the same. So then I multiply again for the 3rd year by 0.935. And I get $19,307. Let's go down. Let's say I wanted to know, well, how much is it worth after 10 years? Well, then an explicit formula would be much nicer. So if I'm going to, sorry about that, Belle. If I'm going to rewrite this recursive sequence in an explicit formula, I'd have a sub n equals my initial amount, 23,620, times my ratio, my common ratio, which is 0.935, raised to the n. So I can plug in 10 for n, and see how much it's worth after 10 years. And I get $12,061.40. So way over here, year 10, worth $12,000. So I can see this curve is going to look kind of similar to the exponential growth. It kind of looks like that growth curve's been flipped about the y-axis to create this exponential decay curve. So a few things about exponential decay. The first thing is when I'm looking at my base formula, which is actually the same thing as growth, y equals a times b raised to the x, except for now the b value is in between 0 and 1. And it's no longer called a growth factor, it is called a decay factor. So because of this x value being in the exponent, I can't think of any x values that I would plug in that would make that y value negative. So as this function travels within our x going to infinity, the function y is going to get closer and closer to 0, but it's never actually going to dip negative, and that's because of my properties of exponents. Remember, if I were to have something, a value raised to a negative n, that's just 1 over a to the n. Doesn't actually make it negative, it just puts that in the denominator. So again, I have that same base formula, y equals a times b to the x. The a value again is just the starting value. So in my example, it would be this 23,620. B is the decay factor. Instead of the b being equal to 1 plus r, it is going to be equal to 1 minus r in this case. You can see it up here. Right here, you see this 1 minus r, where r was the decay rate. That will give me the decay factor. So the two different things. And so if I were going to write this as a function instead of a sequence, I would say y equals $23,620 times 0.935 raised to the x. And that is the function I would use to describe this exponential decay curve. So those are the type of functions we're going to be looking at today. What happens with something that loses a percentage of its value over time instead of gaining a percentage of its value over time? So first, what I'd like to do here, you're going to end up pausing the video in a minute. You are going to say which functions represent exponential growth and which represent exponential decay. You're going to find the growth or decay rate and the growth or decay factor for each one. So here, remember that the rate, the growth or decay rate, that's my R value, whereas my growth and decay factor is going to be the B value. And when I'm talking about the A and the B value, let's just review really quickly. So both exponential growth and decay have this parent function, this base formula. The A value is always the starting or the initial amount, and it is the y-intercept if I'm looking at the graph, because if I were to plug in 0 for x, I would have b raised to the 0, and just remember b raised to the 0 or anything raised to the 0 is 1. So you will always have the point 0a on your graph of your base function, making it a y-intercept. And now this b value right here, this is what tells you if you have growth or decay. So if b is greater than 1, we're looking at a growth function, and hence we've got a decay factor. And if b is in between 0 and 1, we have a decay factor. We will discuss later on what happens if I have a negative b value, and that will be later on. For right now, we're just looking at the b values greater than 1 or b in between 0 and 1. So go ahead and pause the video, and then when you come back, you'll be able to check and see how you did. Okay, welcome back. So what I've done is I have circled the numbers that I'm looking at in my function. Since I know that the b value is what's going to grow, tell me if this is growth or decay, I've circled those and isolated them, knowing that these values in front, these a values, are just initial amounts, and they aren't really going to be necessary for me to answer this question. So in A, I'm looking at the b value, which is 2. Since that's greater than 1, I know this is a growth function. The growth factor, b, is 2. And now my r. Remember that b is equal to 1 plus r for growth, or 1 minus r for decay. So since b is equal to 1 plus r, this means r must be equal to 1. And that implies my growth rate is 100%. Let's look at the next one. I'm looking at my b value of 0.5. Since that's in between 0 and 1, I know this is decay. My b value is 0.5. For decay, I know that b is equal to 1 minus r, so that r had to be equal to 0.5. Hence, my decay rate here translates to 50%. The next one, I have 1.3 for my b value. That's greater than 1, so it's growth, and my growth rate is 1.3. In order for that to happen, my growth rate had to be a 0.3, and that translates to 30%. The next one, D, 0.8. 0.8 is less than 1, so I know that's a decay. My B, my decay factor, is 0.8. That means my R had to be a 0.2, since B is equal to 1 minus R. That means my decay rate here translates to 20%. Now in E and F, this is very nice because if you look, they have the B value written in this 1 plus R form for me. Since I'm adding this in, I know that this is growth. My B value is just going to be the sum of 1 and 0.025, so I get 1.025. My R is just the 0.025, and that translates to 2.5% growth. The next one, my B, is 1 minus 0.4. It's kind of nice, deconstructed for me. So I know I'm going to have decay, because when I subtract that 0.4, I end up with a decay factor of 0.6. My R can be seen clearly as 0.4, which is 40%. So what this also allows me to do is I can have like a spin-off formula for growth and for decay. For growth, I could write this as y equals a times 1 plus r raised to the x. And for decay, I could write this as y equals a times 1 minus r raised to the x. And I feel like these are actually more common to see in textbooks. They like to split these up into growth and decay. But it's nice for you guys to see that the 1 plus r and the 1 minus r, they're just translate to one value when they're simplified that we can call b. And if we know that b is greater than 1 is growth and b is in between 0 and 1 is decay, then we are all set. So now let's take a look at a couple examples. All right, so during the economic recession, which started in 2008, CNN reported that property values were declining at rates as high as 18% annually through the year 2012. So starting in 2008, the property values were declining at rates as high as 18% annually through 2012. We want to find the property values for home 1 and home 2 if their property value in 2008 is listed below. For this example, let's assume this really as high as it can be declining rate. So here my R value is going to be 0.18 for 18%. So if I were to write a model just for these 4 years from 2008 to 2012, I would say y equals my A, my initial amount, is always going to be the starting value of the property. So home 1, it would be this $248,940. For home 2, it would be $563,500. Times B, now my B, I'm just going to go ahead and replace that with 1 minus R raised to the x. I know my B is going to be equal to 1 minus R, and so therefore I'm going to get 0.82 left. So this right here is the same thing as B. You can put 1 minus 0.18, or you can just go ahead and replace it with a 0.82. It's up to you. So let's find the home value for home 1. I would have y equals $248,940 times 0.82 raised to, from 2008 to 2012, that's been 4 years. So when I put this in my calculator, I will see that in those 4 years, the property value has declined to $112,551.19. That's pretty drastic dip there. Let's look at home 2. I'd have y equals $563,500 times 0.82 raised to the 4th. And here I have $254,770.61. Again, I mean, this is really, really drastic. And I know, I'm not sure if it was this terrible in 2008, but I know that a lot of people lost a lot of money in that recession, and I know that property values of homes were a really big contributor in that. So now let's look at the next example. It says in 2014, so now we've skipped 2 years. In 2014, the housing market began to rebound. So let's assume that from 2012 to 2014, it was just stagnant and it just stopped. It says if property values increased at an annual rate of 5.3%, how many years would it take before the two houses were back at their original values? All right, so now we're going back into a growth example, which is always going to be positive for these two home values. All right, so for home 1, the value in 2014 is $112,551.19. So that's going to be what I'm starting with. And they're asking how many years will it take for it to go back to its original value. So I'm looking for the number of years. The value of 2012 was right here as well. I'm going to be starting at 2014 because that's when it says that it starts to increase at this rate. So I'm looking at my Y value, my end game. I want it to be the $248,940 equals my original in 2014. If it's increasing at an annual rate of 5.3, that would mean my R is going to be 0.053, and my B value is 1 plus R, so it's 1.053. Raised to the x. And I want to know what x value makes this true. So for this example right here, what I like to do algebraically is use a logarithm, but we haven't discussed those yet in this class. So what we're going to do is we're going to use a graphing method because you do know how to find intersections of graphs. What I'm going to do is I'm going to make these numbers more friendly. I'm going to go ahead and divide by $112,551.19 on both sides. So when I do that, I end up with a much simpler equation. 2.21 equals 1.053 raised to the x. And now what I'm going to do is I'm going to use my graphing calculator. I'm going to set this equal to y sub 1. That'll just give me a horizontal line. And then I'm going to set my exponential equation set as y sub 2. So in your calculator, when you graph this, what it looks like is you've got a horizontal line, and that's happening at the 2.21. And then you have an exponential growth function here. That's your 1.053 raised to the x. You can color code this for you. And I'm just looking for this intersection right here. What is this x value? And when you do that, when you go in and you find the intersection, you will find the x value here is 15.37. So how many years is it going to take for it to get back up to its original value? Well, starting in 2014, it's going to take a little over 15 years. So we're looking at the year 2029 for home 1 to get back up to its original value. So now that we're in the year 2019, we know that the economy has actually rebounded very quickly, and so this property value had to have increased much more than that in order for it to get back up to its original value, because I believe most houses have rebounded. Let's take a look at the second example. So see if it takes just as long. So in the second example, the value in 2012, it's going to be the same as the value in 2014. We have $254,770.61. So I'm going to take, that is what I want, is my output, and that's going to be equal to my, actually, that's not what I want as my output. What I want as my output is the original home value. I want this $563,500 back. So that is going to be equal to my value in 2014 times my B value is still 1.053 if it's increasing at a 5.3% rate. And let's go ahead and let's solve this using graphing. You don't have to make the numbers more friendly. You can plug these in, but if you do, make sure you adjust your window. So I'm just going to go ahead and do this one step so that I can avoid changing that window to these very large numbers. When I do this division, I get 2.21 again equals this 1.053 raised to the x. And so this is really interesting, and I'm rounding, of course, but since I have the same equation here as I had up here in my home one, I know the solution is going to be the same. When I graph these two things, you can definitely test it. When you go in and you put your horizontal line at y equals 2.21, because I'm going to put this in y sub 1, and then when you put your exponential function in here, your y sub 2 is the 1.053 raised to the x, you're going to see the same intersection. They would have to have the same intersection. They're the same equation, giving you 15.37. So again, we're looking at the year 2029. So I do wonder, if that is coincidence or if mathematically you're always going to get that, because we had these two homes decaying at the same rate and then growing at the same rate. Very curious, something to think about and explore. Okay, one more example. According to population.us.se.charleston, the population in Charleston, South Carolina grew exponentially from 90,620 people in 1990 to 120,083 people in 2010. We're going to write a function to model Charleston's population from 1990 to 2010, assuming the population grew at a constant growth rate during the time period, where P is the population and T is the time. And T is going to represent the years since 1990. Missing a bracket there. Okay, so think about this. It tells me that we grew exponentially, so that means I have to follow an exponential growth model. And I don't care if you use a times b raised to the x and you in your mind know that b is going to be greater than 1, or if you go ahead and you change it to this 1 plus r. It's up to you. I prefer to just leave it like this. It's simplified for me. And now what they've given me essentially here is two data points. If they're asking me to use P and T, I should change this Y to a P for population and my X to a T. So my input is T, time and year since 1990, and my output is P, population of Charleston. So the first data point they give me is that in 1990, in year 0, my population was 90,620 people. Well, I notice this is a y-intercept. If my input is 0, then my output is my y-intercept, my initial value. So they've given me my a value. Oops, let me make this a little bigger. So my p is going to be 90,620 times b raised to the t. And now on the next piece of information, I'll go down a little bit. They have told me that the population in 2010, so after 20 years, the population is 120,083 people. So I can plug that point in and I can solve for my b value, my growth factor. So I'll have 120,083 equals 90,620 times b raised to the 20. So to solve for b, I got to divide first. On the right side, I'm left with b raised to the 20th power, and that's going to be equal to 1.325. And now to get rid of that b to the 20th, I need to take the 20th root. And then I have b is equal to 1.01417. So if I'm writing a function, my function is just going to be p equals 90,620 times 1.01417 raised to the t. And now I can use that model in the next two problems. It says, using the model you found from the last problem, what will the population of Charleston be in 2016? So in 2016, again, the t value is years since 1990. So if I'm looking at years since 1990, I'm looking at t value being 26. So I'm going to plug in 26. And I'm going to get approximately 130,080 people. So still growing. I should put people exponentially. The next one says, now use the population to figure out when Charleston will reach a population of 180,000. So I'm plugging that in for my population. And I'm solving for the time. Again, I'm going to make my numbers more friendly. I'm going to divide by the 90,620 on both sides. On the right-hand side, I'll be left with 1.0147417 raised to the t, and I get 1.9863 on this side. I'm going to go ahead and draw a little graph to represent what my calculator is going to do. So I'll have a horizontal line at 1.9863, and then I'm going to have an exponential growth function. This is the y equals 1.01417 raised to the t, or raised to the x in your calculator. And I'm going to find this intersection to see how many years it takes. When I do that, I get an x value, an intersection of 49.36. So that means it's going to take 49.36 years from 1990. So we're looking at the year 2039, about 36% of the way through that year. I'm going to reach a population of 180. And when that happens, Charleston is going to be in big trouble because we really just don't have a ton of space. We're surrounded by water. So if we keep growing the way, we're just going to have to keep moving out of the peninsula and into the upstate. All right, so now you guys should be set for problem set 5.2.